Okay, so we've proved Newton's theorem for field theory, but let's just spend a minute. To ask ourselves, what would Newton's theorem say for mechanics? Okay. So let's just have a little section here called Newton for mechanics. And what I'm going to do is I'm going to give you a couple of pointers. If you are trying to prove Newton's theorem for mechanics, so try to do that. That's a great exercise. But what would you find? So first of all, what you're trying to prove is not that the divergence of some current is equal to zero, but in mechanics, you'll just be trying to prove that dq dt is equal to zero. You would have the Euler-Lagrange equations, which you know well. And the statement here that the action is unchanged by the symmetry transformation tells you that the change in the action must be equal to now just a total time derivative. So we would have some df dt. And if you go through and repeat the proof that we gave, if you do things correctly, you should learn that Q, the neuter charge now, the conserved neuter charge, should be something like dl dx dot, because the field of the particles, the field is now replaced by the coordinate of a particle times by delta x, and this would be the change of the coordinate under the symmetry transformation minus f. So this would be the neuter charge. So try to prove Newton's theorem for mechanics. If you can get this result, it's very good evidence that you really have understood what's going on. I now want to give a second proof of Newton's theorem. I'm again going to do it in field theory, and you might wonder, why am I giving the second proof? We've already proved it. Well, I think the second proof is maybe a bit more elegant. It's a lot slicker, so that's why I like the first proof. You can see all of the moving parts. This proof that we're going to give now is a lot slicker, but what's nice about it is it generalizes very well to the quantum theory. Okay, so let's now give the second proof. So let's start off. So imagine we have a symmetry. We have a symmetry. What does that mean? Well, that means the change in the action delta S will be equal to zero under the symmetry transformation. So the symmetry transformation, if you perform that on the fields and evaluate the new value for the action, it will be same as the original value for the action. Now I'm going to imagine doing this. So do an infinitesimal transformation. And by transformation here, I could be doing a translation by some distance. I might be boosting by some rapidity, or I might be rotating by some angle. For example, I'm going to do an infinitesimal transformation by infinitesimal transformation, I mean that I've taken an infinitesimal parameter of the transformation. So this would be the rotation angle, the boost rapidity, or the distance by which I translate. And I'm going to call this some infinitesimal parameter epsilon. But I'm going to do something which perhaps looks a bit weird at first. I'm going to say allow epsilon to depend on x. So this is like maybe doing a boost where the rapidity of the boost depends on where you are in space. On Earth, I do a big boost. On the moon, I do a little boost. And close to the sun, I do no boost at all. So it's an x-dependent boost. This is definitely not a symmetry. You know, you can't just do local boosts all over the place and expect that to be a symmetry. It's not a symmetry. And this means that the change in the action will not vanish. It will not be equal to 0. Well, if the change in the action is not 0, what is it? Well, here's what I claim. So my claim is that the change in the action delta S will be equal to an integral d4x of j mu of x d mu epsilon of x. Now, I want to convince you that this is the change in the action. And I think I need to convince you of 3 things. So the first thing I need to convince you is that delta S must be linear in epsilon. So that's the first thing I need to convince you of. Second thing I should convince you is that delta S depends on d mu epsilon. So the derivative of epsilon. That's a very specific thing. And then the third thing I should convince you is that the coefficient of d mu epsilon. Oh, why did it do that? I don't know. Is j mu of x. So I need to convince you of those 3 facts. So let's look at the first point. Okay. So first of all, epsilon is a symmetry transformation. If epsilon is 0, okay, if epsilon is 0, then I didn't do any transformation and the change of the action is 0. So there should be no term that's independent of epsilon. So the epsilon to the power of 0 term should not be here, because if I set epsilon to 0, delta S has to vanish, because if epsilon is 0, I didn't do a transformation and the action didn't change. But even though the epsilon to the 0 term is not there, I could have a term of order epsilon, epsilon squared, epsilon cubed, and so on. But remember, I've taken epsilon to be infinitesimal. So what that means is I can neglect epsilon squared, epsilon cubed, and all of the others. So this first point is true because for epsilon equal to 0, delta S has to be equal to 0, and because epsilon is infinitesimal. Okay, so good. I must depend on epsilon and no higher powers, and there's no constant term. Why should it depend on d mu epsilon? Well, so I've said epsilon is some function of x, but if I choose epsilon of x mu to be a constant, if I simply made that choice, then I am doing a symmetry, and delta S has to be equal to 0. So I have to make sure that if epsilon was some constant, that delta S would vanish. But how do I do that? Well, I should depend on a derivative of epsilon, because it's a derivative of epsilon that will vanish when epsilon is a constant. So good, so I must depend on d mu epsilon. Why? Epsilon equals to constant. Well, this is a symmetry, and that means delta S is 0. Great. And now we come to the final point. Why should the coefficient of delta epsilon be, of d mu epsilon be j mu? Well, let's remember what delta S is. I've taken phi and I've changed it into phi primed, and phi prime was phi plus some symmetry transform, which depends on epsilon acting on phi. And then what is delta S? Well, delta S is just the action evaluated at phi minus the action, maybe it's the action evaluated at phi primed minus the action evaluated at phi. But S at phi primed is Lorentz invariant. S of phi is Lorentz invariant. And that means delta S itself must also be Lorentz invariant. Now, d mu epsilon is a 4 vector. So to make a Lorentz invariant, I need to contract with another 4 vector. So the coefficient of d mu epsilon must be a 4 vector, and I must contract with that 4 vector. So indeed, the coefficient of d mu epsilon must be j mu. And what's the reason? Delta S is Lorentz invariant. Good. So that is the reasoning for why delta S must take the form that it does. Now let's manipulate that form for delta S a little bit, okay? So I'm going to take delta S and I'm going to write it as follows. This is equal to an integral d4x. Then I'm going to write d mu j mu of x times by epsilon of x. And I'm going to subtract d mu j mu times by epsilon. So let's see why these two are equal. Okay, so when I calculate this first derivative, there are two terms. First of all, the d mu could act on the j mu. If the d mu does act on the j mu, I'm going to get d mu j mu epsilon, and that's going to cancel against the second term. So the term of d mu acting on j mu cancels against the second term. So the only term that lands up surviving is when d mu acts on epsilon. But if d mu acts on the epsilon, I've got j mu d mu epsilon, and that is the term that I've started with, okay? So the derivative of the product minus the second term is exactly the expression for delta S that I wrote above. So I haven't actually done anything. So that's definitely an equality. Now, the next thing to note is I can drop this term. Why can I drop that term? Well, it's a boundary term or a surface term. So when we were discussing the Lagrangian approach to field theory, we argued that we can always drop these boundary terms. It just depends on the value of the fields at infinity, which is 0. So in fact, delta S now simply becomes, there's a minus an integral d4x epsilon of x, so epsilon is an arbitrary function of x, times by d mu j mu. Now, let's evaluate this. So evaluate delta S on a solution to the classical equation of motion, or equations of motion. That's on the a solution to the Euler-Lagrange equations. Now, if we're on a solution to the classical equations of motion, that means that delta S is 0, and that means any first order variation vanishes. So in particular, the first order variation that we've been considering, because we just varied phi into phi plus delta phi, under that first order variation, delta S will also be equal to 0. So because we have evaluated on a solution to the classical equations of motion, because of this, delta S is equal to 0. But this expression for delta S has to vanish for any epsilon of x. So that's an infinite number of equations. And the only way that the integral d4x epsilon of x d mu j mu can vanish is if d mu j mu itself vanishes. So this implies that d mu j mu of x is equal to 0. And we have now again proved Newton's theorem. If we have a symmetry acting in our theory, we always have a conserved current. And you know, where did we use the fact that it's a symmetry? Well, in proving this form for delta S, we crucially use the fact that we have a symmetry. And then in proving that delta S is 0, we use the fact that we have a solution to the classical equations of motion. So again, this equation only holds if we have a symmetry and only when evaluated on a solution to the classical equations of motion. Great. We'll continue in a moment.